Let's continue. We will have the first real example. Uh, First, I'm going to draw it on. We'll take a little time for it because we need to be fully understanding how it is going to help the irrotational flow theorem. Imagine that is you have a tank big enough and there is a pipe which is giving a water in all direction like this, and there is a hole in the tank and the water going out from the tank. If you're going to do Navier stock equation, you need, as we discussed before, to define the at the end you need to define the u and v equation, and we assume there is no w, which is mean there is no velocity in in z direction approximation, or it is large enough. So you need to define all of this, and to define it, to have uh, the effect of mu and the shear forces and the effect of sorry, the pressure that will be by del here with del y, etc. Okay, if you start to plug all the equation, unfortunately you don't have enough boundary condition. So to use this theorem, which or this theory regarding the potential flow theory, you need first to understand Navier-Stokes. You cannot use it due to you don't have the boundary condition. Second, to use this theory, you need to understand you are not in the boundary layers, because in the boundary layers there is a rotational flow, or there is non-potential flow. For example, if we have the flow and the flow is going like this, here the flow is zero, which you can go like this. However, if this example will help us later on, if you have a flow like this, so we know because it is diverging duct, so the pressure here will be more than here, but the velocity will be less, and we know the velocity here always zero. But because of there is an adverse pressure, maybe there is will be swirls like this, while after the boundary layer here is a potential flow, here maybe you have swirls. So vortex, or like this, it is not a swirl, vortices which is making like this. Okay, so this theory or this theory cannot follow this one. So first you need to identify that is your solution is not at the boundary layer, or neglecting the effect of the boundary layer, neglecting the effect of the boundary layer in case of you have an adverse pressure, and also you don't have enough boundary condition to start solve the Navier-Stokes. Okay, let's come here to our example. So we know there is a case, somebody, an engineer came to you and told you that is, we have a tank and the tank is filling a tanker, and there is whatever, a lake or whatever, and the lake having a pipe, and there is a storm water coming from the pipe to that tank, and we know that is there is an opening in the tank where the flow is going out. So you will tell him, okay, I don't care, it's okay, but of course, the tank is here fully submerged, so the pipe is fully submerged. Okay, and the tank is large enough, etc. Then you will tell him, okay, it's okay, I don't care, it's okay, no problem. But he will tell you another information. But I am a little bit concerned that is because the water is going like this. Of course, because the amount of flow rate here is different than the amount of fluid going out, there is will be stresses on the pipe. So maybe the pipe will be break, maybe, or what is will be the forces on the pipe, what is will be, you get my point? So you need to study that condition even with a minimal information. Like this is beauty of uh, the Navier stock, like what we discussed before, sliding bodies, step pairing, and even in the potential flow theory. Yeah, this is the beauty. You don't have enough information, or you don't have uh, detailed information yet. You can reach to even the formulas of describing the velocity profile and pressure profile and etc. You can reach to a position like you can identify in each point what is the velocity, what is the direction. So this is the beauty of it. Then you can calculate even what is the pressure is going to be, then what is the forces, like what we discussed in the, and even you can reach to a positions of deciding before doing the CFD. Yes, the answer will be this number, but if in case of the complication of yeah, for example, what we discussed before, the step bearing, if we start to say, the step bearing having some notches and something like this, pre-calculation, you can assume if there is no notches. You can done your calculation or your Navier-Stokes equation. You know that is approximately, I don't remember, kilonewton or sorry, meganewton, as I remember the answer for that one. So when the CFD giving you with the notches, etc., 78 or 82, you know that is this number is correct because you done a pre-calculation manually how it will be. And I don't prefer to write it as a calculation. It is a derivations. CFDs is built on your pre-calculation. It is like a derivations. You are deriving what is will be the equation. Even CFD to do or to take a result from any number or for any case, you need to run at least for like a 2 days, 3 days in case of you are in transient state, or 1 day in case of normal state. Imagine if you're going to do all of this, then after you're going to change back to the 3D model to change it, to change some parameters to reach a position to have another answer. For example, you need to have a 100 mega Newton, for example. Then you change the 3D, then you run again for 1 day. It is a nightmare, but if you've done it with the approximation, you will know before doing anything, just changing the H, the L, or whatever, so you can get how much Newton you want. Then you will plug it directly in the 3D model. So it is not like do calculation after 1 week, then after CFD after 1 week. Ah, no, 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 it is failed. No, 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 it is failed. No, no, it is failed. You don't have all of this time. Even nobody's going to pay to you to all of this work. Like it's like you're going to design an HVAC system, and without knowing what is will be the parameter, or before like knowing anything, just okay, do the calculation, do the half calculation, take the result, put the result, then figure it out. Okay, okay, the load is 100 ton. Then after you will go to whatever, any entity. No, no, 100 ton is too much. Okay, okay, change the U value, change the calculation, change. But in the habit, it is very easy to change the U value. But imagine you're changing all the steps in the CFD. No, it is now it is 90 ton. No, 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 reduce it more. How much you want? 50 ton. So you make a trial and error each time, and each trial and error will take 4 5 days. No. So let's return back to here. Okay. Here we know, sorry, here we know that it is a condition. Okay. So we need to discuss it first because this one is central, or it is like a source and is the sink. For sure, we're going to use R and theta. But remember, R and theta, we are returning to R and theta, or X and Y. There is no any difference between each other. But we need to be smart to know how going to be the derivative. Uh, the rotational flow theory is depending on derivatives. Navier-Stokes equation, its solutions depending on integration. Okay, so we need to know what is going to happen. Okay, let's call back. Okay, I jump away. Oh, by the way, this is example, but this is going to example we're going to follow. Okay, which is source and thing, but to follow as big this one. So this one will not be source. This will be a vortex. Okay, giving a vortex like the irrigation. You know the irrigation nozzle. There is an irrigation nozzle which is mean a pipe, and there is a cap like this, and of course there is a cap and this seal, and another cap, and there is seal, and there is a nozzle giving the water like this, and a nozzle giving the water, and this is rotating while the water flow. When the water flow, it is rotating, so it is can give that. Okay, uh, as a vortex. Okay, so this will not be. This will be as a vortex, just to follow the same sequence. Uh, because in this example, I'm going to do it in two ways, which is to give you an idea. If you took that way, what's going to happen, and if you took another way, what is going to happen. Okay, okay. So we know that. Okay, okay. Need to turn back. Yeah, here. No, here. So blocks, we know vortex. Please take it right at the side. By the way, you can use the phi or ipsi, the potential or the stream function. Both is the same. Potential function plus potential function equals the total potential function, or ipsi plus ipsi equals total stream function. Both is the same. But you just remember you're going to make derivative. How? What is the derivatives we're going to make? For example, if you select ipsi, so in polar, the UR and so the UR and U theta. You are going to make a derivative in theta, and U theta make a derivative in R. So which is mean you are going to have ln R, you'll make derivative in R, of course, ln derivative of ln R 1 over R. It is very basic. يعني. Even I didn't write it here because it is you need to know. I will not write all the derivatives. However, it's okay, but you can. There is something also to learn. Where it is. So it takes too much long, but however. 1 over x. Okay, this is very simple. And by the way, there is even if it is 1 over x plus something or etc. For example, even maybe I didn't write it even. Maybe later we're going to find it in much way details. For example, if you have ln r plus or ln x plus y or ln r plus something or over something, so the derivative of it is the same function above divided by the derivative or sorry, the derivative of the above divided by the, here it is written. Yeah, okay. So ln x squared plus a is constant, so it is the same function above in a derivative of it divided by the same function. Okay, just this is the rule of ln derivative. Okay, let's return back. So let's describe what we have. He start to say that we have a vortices here, and the idea here is there is a thing or the equation. Let's open the, so let's return back. Okay, I couldn't find it, but however, as written from the textbook, however, see, it is a simple question. You have a big water tank. Forget this one now. It is very simple than I was planning to explain. However, you have a big tank, whatever. In a point of it, there is some source of water like this, and some source of water like this. Okay, and you need to check the stream function. Of course, the stream from here will go like this, then will go out, and from here will go like this. Just an indication. Okay, so you need to check what is the velocities, and here will go like this. So you need to check what is the velocity profile, etc., etc., etc. You need to get sorry, u function at any x or y or z or r or theta. Okay, we assume that is in the middle of this one is axes what we have. Okay, so we assume that is x is here. Uh, the information is the vortex is over b from the source and from the center axis of, and the source is a distance of b. Of course, you can to have two sources, etc., etc., etc. Okay, so we have, as we explained, either to use a root of r and theta or to use a root of x and y. You have the both option. This is okay. Let's check r and theta, how it is we're going to reach. Then we'll discuss which one is which one is better. First, we need to write the psi as it is. But I select psi. It's okay. Psi for 1 and psi for 2. Okay, let's return back. Psi for vortices is minus, which is the magnitude, and we agreed that is the magnitude, which is minus 2 by magnitude. It is equal to q over L. Okay, just because if you put 2 by, so 2 by 2 by, so it is, and minus by minus, so it is q over L. This is the psi, q over L multiplied by ln r. It is the psi function. Okay, and this was the derivation which is we discussed about. So take the psi, which is minus magnitude of 2 over pi, and you will assume, or he will tell you, for example, the magnitude here is 1, and the magnitude here is 1. So you have the source, and the source, by the way, don't forget. And if you go to the source psi is magnitude multiplied by theta plus c2, c2 is 0. Okay. Okay. So now we are going to return. So magnitude theta, the second psi for the source, and magnitude minus magnitude over 2 by ln r for the vortex. See, psi total is this function. We know that is ur and u theta, ur equal 1 over r del psi by del theta, and u theta is minus del psi by del r. It is from the, 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 the basic which was discussing the definition of the potential flow. We use the polar coordinates, we used the polar coordinates, and we used this one. Okay, so it is very simple, but remember, I know that is r here is different than r here. Yes or no? Yes. Yeah, it is different because the center, because this equation and this equation And even this equation, it is or this one based on the center at the center here, and this one the center of axis for the source at here. But we know that the center of axis is shifted, so we need to re-manipulate whatever we already understand regarding re-manipulation. So psi1, which is len r, we know now psi1, which is len r, it is minus magnitude over it is 2 pi, but I will tell you why, because we know that is r equal for 1, which is here, is equal to x. It is the same x, so there is no shift in the x directions. It's the same x plus y, but y, it is y plus b. So y here is y plus b all squared. So all under root. So len r, it is root of x squared plus y plus b all squared. The under root is 1 over 2. In len, you can shift 1 over 2 to down. That's why it becomes 4 pi. So minus magnitude 4 pi. Len x squared plus y squared plus b squared plus 2yb. I make algebra. Okay. Same concept for psi 2. It is the same. Y here, it is from here, it is minus b, because the definition here, if it is 0, but for here, this one, it is this one 0, but it is for this axis, it is y minus b. Okay. Same concept. So add it together, please. So it will be the psi function. This is the actual psi function is minus magnitude 4 pi len plus magnitude. Okay, very simple. Now we need to decide which path we need to go. We will go to this path, which is cylindrical or polar coordinates, theta and r, or we are going to use x and y. Both is the same. It is up to you. Because we already have a lot of functions in x and y, it is preferred to go with x and y code, which is the second code. But I'm going to continue with the like somebody didn't figure it out and say, no, 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 it is, I'm going to use because it is theta and r, here it is function of theta and r, and here's function of, I'm going to use polar coordinates. Okay, also cylindrical coordinates. Okay, you need to return back to the definition of r. R is equal x squared plus y squared. Good. So this term is r. Okay, r squared. Good. And you need to know that y is equal r sine theta. So it is 2 r sine theta multiplied by b, and x is r cosine theta. Okay, so any x alone, r cosine theta, any y alone, it is r sine theta, and continue. Then you will write r squared plus 2rb sine theta plus b squared plus m tan inverse r sine theta minus b over r cosine theta. Then you make to get u theta, so it is minus del psi by del r. Make the derivative here. Okay, derivative of len, easy. We said that is derivative of above in respect to what you are going to derivative divided the same of above. Okay, we make derivative of r, so it will be 2r. Here there's no r, here r, so it is 2b sine theta. This is constant 0 plus the same equation. Okay, then derivative for r for this one in the tan inverse. Tan inverse derivative, I just wrote it here. Tan inverse derivative, if it is 1 over b, 1 over x or ax, which is mean the derivative item in the base or in the where it is. Yep. So we are going to make a derivative for what? We are going to make the derivative for r above, which is assume it like this: x plus b or x minus b over x or over 2x. Okay, tan inverse for this one. Which is going to follow this one. So it is something multiplied by x plus b over something multiplied by x plus c. The derivative for this one is minus b d plus a c, it is all the constants, divided by ax square. Of course, you will take, if there is a is 1, keep it 1. If it is in minus, you will keep it in minus. Plus xd plus c, all here square and here square. So you will make the same. Then you will get this one based on this one. By the way, this is u theta. This is u theta. And you can, by the way, use the same definition of the psi for ur, which is it is 1 over r del psi by del theta. But just to be in the picture, that is, if I make this one and a derivative in theta, you cannot do it. To shorten the distance, you cannot do it. It is impossible to do it, not because of here, because you are making derivative of ln sine x, for example, derivative of ln sine x. There's no direct, so it is impossible to do it. Even here, you are making derivative for tan inverse, not x, tan inverse sine x divided by cosine x. So you cannot do it. It is so you will be forced to to write the phi function. Write the phi function, the same concept, the same procedure. Then you can make a derivative 2r. So there is no, so to get the ur, because psi u theta is the derivative of del r. Ur in phi function is derivative of del r. So good. So we will not make derivative in sine thetas or cosine thetas, which is under the ln, etc. So you can make the derivative, which is you can take the equation of ur. Okay. Then after finishing that equation, just to know is your uh, uh, is your assumption or whatever, or you need to take some numbers or just to manipulate to understand what is you was doing is correct or not. See, here is this point, this is going up, and which is mean the ur, which is let's store it here. This is the x, sorry. This is x and y, and you know there is a velocity r, and there is a velocity u theta, and you need to check it at the center. What is the velocity r at the center, and what is the velocity u theta at the center? Just bear with me, okay? So you just apply at x equals 0, y equals 0, which is r equals 0, and theta is equal 0. But bear with me now, because if y equals 0 it's tan inverse 0, which is tan inverse 0 is 0. Okay, so just plug the numbers, write r0 theta 0, you will get the numbers, tuck tuck tuck. Then u theta is equal what? U theta, this is 0 minus mb. Oh, this is u theta. Okay, so you will write sine theta. Sine theta is so this term is bye bye, and only remaining this term, b over b squared, it is m over b. So at the center, u theta equal minus mb. Okay, u theta equal minus mb, and you are UR from the equation what we have, same concept, which is, by the way, UR is here. You have here M multiplied by all of this plus this. So it is, here is 0 and here is 0. So it is 2 by b squared, 2 by b squared, and magnitude multiplied by b by b. And by the way, this r and this sign is this 0 and this 0. So full term is 0 here. So this full term is 0. Okay. So the remaining is what? The remaining is pi over 2 by b. So let's imagine this answer. So based on that, we know that is the UR, oh sorry, the velocity in R direction due to, at this point, it will be only and only from the source. Yes or no? Yes. Because this one is making a vortex like this, like this. It is a circle like this, which is will be, if here a vortex, which is mean there is a repeated circles. So when you will reach here at this center, there is no vertical velocity, it is only tangential velocity. So the tangential velocity, or u theta, is only from here. And if this is the source, the only vertical velocity is from the source. So there is no vertical velocity coming from the vortex, as there is no tangential velocity coming from the source. And if you go into the definition of the source from the block, for the source, we know from beginning that u, or the velocity, will equal to m over r, and we know that is the velocity here will be equal to u theta here will equal to, where it is, magnitude over 2 by r. So u theta should equal this number, or multipliers of these numbers, and u r, or the v here, should equal multiplier of this number. It is a must. So let's check our solution. Yes, it is a multiplier of this number in minus b minus 1 over b, and yes, it is 1 over b. So yes, ur is only from this, and u theta is only from this. Okay. Now this is very long procedure and very headache. So imagine that is if we are going through the second route, we didn't decide to go with theta and r. We decide to continue in x and y and z. Okay, we reach to this two equation in psi's, and this is the full psi function. And we decide to continue in x and y and z. In x and y and z, it is okay. U, which is in the x direction, is del psi by del y. So make derivative in y. This is very easy. Y and on y. We discuss here the rule of it. And in this one, we discuss the rule of the length. So you can easily get the u function. And same v, it is del psi by x. It's the same concept. There's no sines, cosines inside the tans, inside the tan inverse. You get our sine, cosine inside the length. So we never been forced even to go to the phi function or the potential function. So see, we reach to u and v. Same concept. I need to check the u in x direction and v in vertical direction. Apply x and y 0. Same. We reach to the same result. And in v, with the same result. And if you need to know the magnitude of the velocity as a magnitude, it is this velocity square plus this velocity square under the root. And if you want to know what is the angle of that magnitude, it is just v, which is present the y direction, by divided by u x direction, tan inverse, to get the theta. Now we have a good point, that is, for example, if I told you here there is something I need to check what is the flow rate here, or what is the pressure here, or whatever, you can use this one. B over rho, velocity magnitude square over 2, gz, which is the difference, it is equal constant. So you can apply that velocity in a position and another position with knowing a certain pressure level. For example, we know, for example, an information that here is the pressure is equal x, y, z, or whatever, and here is the pressure is equal, or we don't know the pressure here. So apply equal constants, which is mean this one minus this one equal to this one. So you'll get the answer of what is the pressure going to act at this point, and even what is the flow rate. Okay. This is just to check what is the pressure we need to do, what I already discussed. Okay, so we get the first route, long route. We take the second route, which is very short. Is there shorter? Yes. In case we don't seek for the velocity profile itself, I don't think about the velocity profile. I just seeking for the velocity only at this point. That's it. Nothing more, nothing else, nothing anymore. So based on the definition, which is I know here is the velocity only from the source, and here is the velocity tangential or in the x direction. So the velocity in x direction only from the vortex, the velocity in y direction only from the source. So I can imagine this one is not there, and I can imagine this one is not there, and apply it, then get what is uh, the velocity here. So I can see that is u theta is only this one from definition of the vortex, and this u r is from definition of the source. Then multiply it, then you get my point. Then that's it. Why I can do it? Because it is velocity. We agreed that is potential function, psi function or stream function, and velocity. We can add it, we can manipulate with it, no problem, because it is a derivative functions. Okay, so I can reach directly to here based on that case only, but it is not for general case. Okay. Okay. Now we will go to a little bit complicated, little bit complication. So we have an example that somebody going to tell you there is, for example, a sewer pipe or a stormwater pipe which is injecting in a tank, big tank, okay, and there is an outlet from this tank, and this pipe is giving a water in all direction. Like if you have a pipe and the pipe for a cap or something, then the water, well, this is a cap or something, then the water start to go like this. Okay, so they need to know what is the force is going to act on the pipe. Is it safe? Is it not safe? Is it etc. And they just told you that they know that this pipe giving a magnitude of 1 and the sink magnitude of 2. How you can get it? Magnitude of 2, it is flow rate, by the way, which is a number of the flow rate. It is a number of flow rate. Okay, so they know how much flow rate he's going to inject. He knows what is the flow rate going to be out based on the height of the water, maybe, or something. Okay, from the height of the water, he knows the flow rate will be like this, and he will assume that the height of the water in a short period of time it will be constant or something. Okay, so he needs to check what is the pressure going to act at that condition, or what is the forces on that. Okay, good. Now I just described something. There is a tank, which is means it's a wall. We didn't discuss anything about the walls at all. يعني potential function, it is discussing about source, sinks, vortex, a uniform flow. Wall, it's not a function, it's not a fluid itself. So to simulate the wall, you need to manipulate and to think more. Imagine if you're going to have an opposite source. If this one at B and this one at B, so the opposite source will act like this, which is will create the wall. You know, tell me the sink. Okay, he told you that they have a sink only from here, from the top. When we make a full sink, which is going to like this, So it will simulate the mirror of it. So the wall will be correctly simulated. Okay, this is how we're going to think. Okay, and to simplify what we are doing. Okay, let's go. So pipe of the water, we agreed M, sink, wall. So we need to add another one to simulate the wall. We know that is psi 1, it is source m theta 1. Just write 1 now because we're going to have one theta and another theta. Okay, why? Because I'm going to have one source here, one source here, so this theta is different than this theta. Okay, and psi 2, it is sink. So psi 1, it is m10. It's just theta. Just write it how it is, as we agreed before. It is y plus b over x. Psi 2, which is at the sink here, it is minus 2m theta 2, which is, because it is the center, it is minus, it is 2m tan inverse y over x. Now there is one point. We need to remember that in case of source, it is plus, in case of minus, in case of sink, it is minus. So while I am writing source 2, it is should be a minus. Okay. Then theta 3, it is very easy, which is here, which is minus b, y minus b over x. Psi function, it is full psi's, psi 1 plus psi 2 plus psi 3. It is very simple. Then it is, you can, by the way, it is recorrected here, but this one should be in minus, and this one minus 2. It is not written. This should be in minus, and here should be in minus. Just forget. But however, here it is corrected. Here it is correct written. So v equal del psi minus del psi by del x, which is will be minus, and minus is plus, and minus. Okay. So you just make derivative in x. Voila, we agreed that is we are going to follow in Cartesian coordinates. It is much easier, and so v equals this equation. Before to continue, we need to check something, because we know this one is a wall, and we know the only velocity going to be here is like this, tangential, but there is no any vertical velocity. Otherwise, there is no wall. That means the water is going like this. So we need to see our assumption or adding a source point. Is it simulate whatever it is correct or no? So apply at y equals 0. So at y equals 0, by anyhow, we need to know, or we need to check that is v must equal 0. Put y equals 0. You will find here 0, blah, 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 b over this term. This fully 0, b minus b over this term. You will find this term minus 0 plus minus this term, this by this. So v equals 0. So our assumption is correct. Now, for u is with del psi by del y, derivative in y. It is very simple. It is nothing. Okay. Now we'll turn back to our question. Okay, we need to check what is the force is going to be. Okay. This is how it will look like. This is a pipe with a lens with velocity at the edge and the velocity at the center, and the diameter, it is like a delta. Okay. So to know about the forces, which is we already discussed it before, but we're going to open it. Oh, I don't know, discuss it or no. Imagine that is you have a pipe, and there is water is going out like this, of course, in all directions, etc. Okay, so which is means there is a resultant force in this direction. Simple. So based on that, based on that, so to know what is going to be act on the pressure or the forces on the pipe, we need to know what is the velocity difference. Yes or no? Yes. From here and here. See, there is a velocity here and there is another velocity here. In balance of these velocities, there is a force, which is mass multiplied by delta V square, and which is V1 minus V2, because this is a source again. We'll go here because velocity in all directions. So here, for example, there is a velocity equal 10, or like this is 10, and in the center, the velocity is equal 1. It's just an assumption now. So because there is an ill balance in the velocity, or so which having more velocity is going to have big reaction, and of course, but this big reaction will be in this case, and this reaction will be in the, maybe it will be in this direction case or something. Okay, so to apply it, the mass of the water in this area, it is by r square l multiplied by rho. V1, it is very simple, will be act on y equals 0, b y, so x equals 0, or b equal y equal b at the center. Okay, and v1 is not the velocity up or down or left or right. It is the magnitude velocity, as we agreed, because we're not going to check only up or right, because maybe the force will be like this or like this or like this based on the direction of the velocities. So we need to calculate at x equal 0 and y equal b at the center what is the magnitude of the velocity. Okay, just plug the numbers and you will get. We'll repeat it again for x2, which is at the edge, which is x equals 0 and y equal b minus r, which is the distance here. Okay, plug the numbers, you will get this equation. Very simple. Okay, so square of this equation minus square of that equation multiplied by this is the force. So square of the equation minus the square of the second equation multiplied by this one is the force. So when he knows the flow rate and the radius of the pipe and the same, he can know what is the pressure going to act on the pipe, or what is the force is going to act on the pipe. Okay, this is, I will go very quick on it in it because it is way going to be repetitive. That is, I have a vortex and I have a vortex also as well. To simulate a vortex, or the question is if you have a vortex and this if you can see, it is not a vortex which is parallel circles, it is from the center going out. It's very tricky. So it is not the vortex what we have, which is circles. It is circle but coming from the center, but we can simulate it as a source plus vortex. Agreed. Then he told you, no, and also I have a wall. So this source plus vortex. And I have a wall. So we need to create another one, but which will create in the opposite direction. Okay? So we will have 4 psi functions. 1 is source, 2 is vortex, 3 is source, 4 is a vortex, but of course in opposite direction. Let's agree about something. First, the source, both are sources. So it is okay. Same techniques, plus A minus A. Now, the vortex, this is the equation of the vortex, but because this one should be in opposite direction, it is a mirror, so the minus should be plus. Okay? Same techniques. Ellipsize, full ellipsize. Of course, again, we're going to select the Cartesian coordinates by del x, makes the integration. Check at the bed, check here the wall is correct. Apply at y equals 0, y equals 0, you put y equals 0, you check, yes, it is equal 0, so your assumption is correct. Then you're going to calculate v2. It's the same concept, is same questions. Let's assume it like this. We need to know what is the pressure is going to act here, or what is the force. So the same concept. Sorry, you will get first. You you will get here u function. It is the partial derivative in y. Very easy. Same technique. Same technique for the force. Apply at center. Apply at r. Blah blah blah. So it is v2 like this. So v2 like this. So the force is square of the first one minus square of the second one. That's it. Okay. Okay. Till now is all the examples regarding the potential flow for an applicable application, which is you are creating the psi function or the phi function. Now we have only one example, but I didn't put another one, just one example. It is for illustration in the opposite case, which is mean you have some function, but you need to imagine this function or this potential flow function or this psi function, what is going to present. So what is the mathematical techniques we need to do to understand what is this, and even to try to get some fundamental equations or formulas or derivative of it or derivation of formulas. Okay? Assume that somebody told you I have a fine function which is phi equal minus magnitude ln r. You will tell me, yeah, we know it. Just go back some paper or some above. Yeah, see, it is. It is. Yeah, this one. Phi function, our potential flow function, is m. It is because it is in positive, it will be source. If it is in negative, it will be sink. So we'll just, yeah, it is source of sink. I tell you, wait. The idea from the example is not because it is minus, so it is sink. I tell you, wait. No, the idea is not to just write it. We know it. Yes, we know, but imagine that is you have another complicated function. So we'll go just so for you. Okay, you need to get the velocity function for in r in theta or in x and y, but because you don't know what is how it looks like, you cannot change from r and theta to x and y because you don't know how it look like. Even you assume you don't know what is this flow. You have only an equation. Because you have only an equation, you cannot say, yeah, I'm going to change from r to theta to x and y because it's easy for derivative and easy for no, don't do it. How you'll do it? How you'll know? Because when you put r, it's equal x square plus y square under root. Maybe x is x plus a and y is equal y minus b. You don't know where is or still you cannot even assume it because you don't know how the flow is running. Okay, so you will follow as it is. So you know this phi, you know u r is del phi by del r. Just make the derivative easy. You know that is u r, it is 1 over r del psi by del theta. You know that is there's no the what so you will get del psi by del theta minus equal to minus magnitude. Why we didn't make the derivative of this one in theta? bear with me. You can do it, by the way. You can do it. So make a derivative of it. So u theta equal 0 from here. And you will trying to get the psi function even and write it. So, okay, tell me, what is the technique? The technique, when you have only an equation, you try to bring all other equations. You need to have the stream function to imagine it, to imagine the flow. You need to have the stream function. You need to have the velocity in r direction. You need to have the velocity in theta direction, and you have the potential function. So you need to have four functions, okay, to imagine what is the flow. So this you have it. This we got it. This we got it from this one. Now the psi function. Psi function, you know it is from this equation. You know it. So del psi by del theta is minus magnitude. Okay. Now you need psi. Integrate. So it is minus theta plus a function of r. We don't know what is a function of r. Still, okay? Okay. Still also you know that del psi by del r should be equal u theta. And you know u theta is equal 0. You just get it. So fr dash, which is means the derivative of fr, because it is should equal 0. If a derivative of a function equals 0, so that function for sure it is a constant. Okay. So we can write that as psi is equal minus magnitude theta plus a constant. And u theta is 0. What do we understand u theta is 0? U theta is 0, which is mean this fully radial flow. There is no here. There is no rotating flow. It is only radial flow. Only the velocities in r. No u theta. So all the flow is radial. This is the first information we can get. Second information, because psi in negative unit, psi in negative unit, whatever you're going to change theta, psi in negative, which is mean that is the flow inwards. The flow inward. When it is negative, the flow is inward because stream function is showing to you where is the flow going to go. So if it is in negative and the center in r and theta, and if this one is r and this one is theta, so this is the center, and the psi function always in negative, which is mean it is going to the center. If you anyway you're going to the center. So we can understand first there is no rotational flow, and it is all radial, and all the flow it is to the center. So voila, make this one, make all the flow to the center. There is no rotational flow. And from the definition of the potential function, it is the vertical lines or on all the stream function. So you can write that the psi function should have a vertical line like this. Okay. And to calculate the radial velocity, it is very easy. We agreed before to calculate, or not we agreed, we still didn't agree, but to calculate, I want to know what is the radial velocity, what is the velocity is going to have, etc. We know at the end that is the mass flow rate is this one, but bear with me, okay? Why? Because still we know all this information from this function, but assume you don't know it. To calculate any velocity when you have a, a mass flow rate, for example, from this area or from any other area, you need to check what is the radial flow here, what is the radial velocity, and what is the radial velocity. Assume this is a surface, and there is a velocity. So the mass flow rate is rho v multiplied by area. But V, it is a cumulative V, which is all around, which is mean, okay, taking d theta, what is the velocity, and integrate from 0 to 2 pi for the radial velocity, you will get what? You will get the full, and that's it. Okay, so it is integration from theta equals 0 to 2 pi, u r d theta, and this is a mass flow rate. Of course, there is rho, by the way, but, okay, so it is equal to 2 by r vr. So vr is equal to, of course, the 0, it is missed up. Vr equal what? So Vr equal mass flow rate divided by 2 by R. Okay? And we can assume it, or as we know, that is mass over 2 by R, or mass equal 2 by magnitude. So mass equal minus 2 by magnitude. How we got it? Here, where it is. Yeah. We know from this equation that is UR equal this. So just put it minus this one, put it, then you will find it. Minus magnitude over R minus magnitude over R. So M equal 2 by magnitude. Just M equal 2 by R minus magnitude over R, R by R. So it will be minus by magnitude, which is the mass flow rate is minus 2 by magnitude is the mass flow rate. And yani, this is if you're going to calculate what is the mass flow rate. Okay, so by the way, and this number already we took it for granted. If you can remember the last or the first pages, that is we wrote it like this before, and we wrote it like this before. Okay, so it is very simple, very straightforward. But how even we can get the equations, even with one equation, I can get everything. I can get the mass flow rate, I can get the velocity, UR, UV, and I can even imagine by the special stream function. Special stream function going to make you imagine how the flow rate. Okay, this is later session because this is a totally complete different subject.